Hey guys, welcome back to another AP Chemistry video. Today we're talking about Unit 8. This is about acids and bases. Okay, so you probably heard of some of these terms before, but we're going to talk about what everything means and how to do some of the math with this, because there is going to be some math, as usual. So some of the vocabulary. We'll talk about acids, bases, strong acids and bases, weak acids and bases, electrolyte, conjugate acids and bases, pH, POH, amphoteric, polyprotic, neutralization, titration, analyte, equivalence point, half equivalence point, indicator, and buffer. Okay, so if you're in advanced chemistry during 10th grade, you actually have done a titration reaction before, so you've done part of this before, but we're going to talk about a little more detail. And also as I go through this, I will be abbreviating some of this. So acids are normally A or HA, bases are B, can become HB plus. Okay, strong acids and bases, strong acid, strong base, weak acid, weak base, and the same thing with conjugates, conjugate acid, conjugate base. Okay, so you'll see some of those abbreviations as we go through this. So starting off with the pH scale, remember that we do have a pH scale that goes from 0 to 14. Note on this one, 0 is on the right, 14 is on the left. Okay. At the center, we have 7. 7 is considered neutral. Okay, it is not acidic or basic. Our blood is pretty close to neutral, but it's not exactly neutral. Okay. As we go to the right, closer to 0, it becomes more acidic. Examples of acidic things are any citrusy. So grapefruit, lemons, any of that citrus is going to be acidic. Sodas are acidic. And then, of course, anything with acid in the name, like batteries, battery acid, hydrochloric acid, those are acidic compounds. If we go greater than 7, going towards 14, that's considered basic. So things like seawater are basic. And then the cleaning supplies and like household cleaning supplies are typically basic as well. Things like bleach and lye are more common. Lye is used in soap. Bleaches, if you get a container of bleach at the store, it normally has a warning on it saying to wear gloves and to avoid skin contact, because a strong base, it will irritate your skin. Okay, so this is a pH scale. It just measures from 0 to 14. It tells the strength of the acid. So the smaller it is, the more acidic. The bigger it is, the more basic. We do also have, and we'll talk about the word POH here in a minute, but we do have a POH scale, which is the same thing, goes from 14 to 0. Okay, it's the same scale. But for this one, if it's a smaller number, that's going to be a base, larger numbers an acid for the POH scale. Okay, so normally we do not use the POH scale. We normally use the pH scale when we talk about things, but you might see that here and there. Okay, and one last note for this, you can have a number that's less than 0 or greater than 14. You normally only see that with math though. If some of the examples in your practice, I just picked a random number and it gave me a pH or of greater than or less than 0 or greater than 14. You only see it in math. In reality, those are too strong of an acid or base, so you wouldn't really see those. Okay. So definitions for acids and bases, we have 3 different definitions. We have the Arrhenius acid. Arrhenius acids produce H plus or H3O plus. The base produces an OH minus. And a note for that, if we look at water, water on its own dissociates into H plus and OH minus. 2 waters together dissociate into H3O plus and OH minus. They both make the OH minus, that's the basic side of it. But one of them makes an H plus and the other makes an H3O plus. H3O plus is called the hydronium ion. Okay. It is essentially the same as H plus. Okay, so you will see those used interchangeably. The only reason it's different is just based on how many waters you have dissociating together. Okay. Our second definition is for Bronsted-Lowry acid and base. The Bronsted-Lowry acid donates a proton, the H+. A Bronsted-Lowry base accepts that H+. And then for Lewis, a Lewis acid accepts electron pairs. A Lewis base donates electron pairs. And what that looks like for the electron pairs is if we have an acid like CH3OH and a base like NH3, lone pair there. What happens is this hydrogen is going to leave, but the electrons go back to the oxygen. So that oxygen is accepting the electrons. Okay. After that, these lone pairs on the nitrogen are going to come and take up that hydrogen. So it's giving away the lone pairs to the hydrogen. It's a donor. Okay, so that's what it means by an acceptor and a donor of a lone pair of electrons. All right. So talking about the strength of acids and bases, on the right here, this yellow table, or the yellow box, you have your strong acids and bases, okay? You do need to memorize these strong acids and bases. They are important. Okay. So our strong acids, we have some polyatomic ions. So we have HNO3, H2SO4, HClO3, and HClO4. Those are your strong acids that have polyatomic ions. Then you have three with halogens, HCl, HBr, and HI. HF is not a strong acid, it's a weak acid. Okay, but the other halogens with hydrogen are going to be strong acids. For your bases, we can also separate this into two groups. Your first group is group 1 elements, so lithium, sodium, potassium, rubidium, and cesium. Those with the hydroxide, the OH minus. So OH minus is hydroxide. Those are strong bases. And also group 2, calcium, strontium, and barium are strong bases. Note here that magnesium is not a strong base. Okay. So make sure you memorize these. Group 1 and group 2 bases, not including magnesium, are strong. And then know these strong acids. Okay. But in general, talking about the relative strength of acids, they are stronger if they are more electronegative, if they are larger, and if they can be stabilized when a proton is lost. Okay, we'll talk about the third one here in a minute. And for strong acids versus weak acids, or strong bases versus weak bases, strong ones completely dissociate. So an example of that is here. You see there's a full arrow there, a single arrow going to the right, because it's completely dissociating. When it completely dissociates, it makes more products. So more products means more ions, making it a strong electrolyte. Okay. Weak acids and bases partially dissociate. So there's an equilibrium arrow. Remember, equilibrium arrow means it's going both forward and backwards at an equal rate. Okay, so anytime you have a weak acid or a weak base, you have an equilibrium going on. And then just as a last note for this slide, we do have percent ionization here. Percent ionization just tells you the percent that your acid or base ionized, how much of it broke down, how much of it became a product. Okay, so strong acid or strong base should be 100%. Weak acid or weak base will be smaller. The stronger it is, though, is closer to 100%. Okay, all you do to find this out is you do your product, so your H3O plus at equilibrium, divided by how much acid you started with. Okay, so the example for this weak acid here would be your H plus at equilibrium, remember these are concentrations, divided by your CH3COO minus at the start, the initial number. Okay, it's the same thing with the base, except with the base, it would be your OH minus divided by your base initial. Okay, so the example here would be OH minus divided by your NH3, so OH minus at equilibrium, NH3 initial times 100. Okay, don't forget the times 100 to make it a percent. Okay, this equation is not on your formula sheet. You do need to know this equation, but it's a simple equation. Okay, it's your product divided by what you started with. All right, let's do some examples with this, some practice questions. For this first one, we have this equation that this reaction, HX plus Y minus goes to HY plus X minus. We have a KEQ greater than 1, and it's asking us which is the strongest acid in this reaction. Okay, so first let's just start by labeling our acids and bases. If it has an H in the start, it's normally an acid. Bases do not have it. Okay, so we have our acids and bases. We can eliminate the bases. To determine the strongest acid between the two of these, we're going to use our KEQ. Remember, KEQ greater than 1 means that we're going to the product. Okay, that means we're going in the forward direction more than we are to the reverse direction. Okay, or we have more product than we have reactants. So remember, a strong acid means it dissociated more. Okay, if it dissociated more and we have more products, that means HX is going to be a stronger acid. Okay, so if our KQ is greater than 1, our reactant is stronger. KQ is less than 1, our product is stronger. All right, the second question here, we have these two compounds. We have HClO3 and HClO2, and it's asking us which one of these identifies the stronger acid and correctly identifies a factor contributing to that. Okay. These kind of questions, as a test-taking strategy, they'll do two parts. So the first thing is at the beginning of the question, or the answers, they'll have the two compounds. So A and B is for HClO3, C and D is for HClO2. At the end, they'll have two reasons that are same. So we have Lund dispersion forces, and we have stability. Okay, so if you know off the bat, we know, say that one's the right answer, we can eliminate C and D and bring it down to 50-50. But we don't know that yet, so let's walk through these. Okay, so A says that HClO3 is stronger acid because molecules experience stronger London dispersion forces. B says that it's a stronger acid because the extra oxygen on the chlorine stabilizes the conjugate base. Okay, so what we mean by stabilizes is if we have this atom here, or the molecule, and we lose that hydrogen, we can draw resonance structures, right? That single bond can go to the top, or it can go to the bottom right. Okay, so we can get 3 resonance structures from this molecule. From the one on the right, if we lose that oxygen, we can get 2 resonance structures. Okay, don't forget how to draw those resonance structures. Okay, so looking between Lund dispersion forces or stability, the stability will have a greater impact on this. So we know A and C are out because we want stability. So the only thing is HClO3 or HClO2 stronger? Okay, so HClO3 has 3 resonance structures, right? 1, 2, 3. HClO2 has 2 of them. The more resonance structures you have, the more stable it is. So since HClO3 has more resonance structures, it is more stabilized. That is going to be our answer. Okay, so our answer here is B. All right. Okay, moving on to conjugate acids and bases. A conjugate acid comes from a base being protonated, so a base gaining an H+. A conjugate base comes from an acid losing that H, being deprotonated. Okay, so conjugate acid and base have similar formulas to what it started with, but a different number of hydrogens. Okay, and they'll have a different or the opposite strength. So it's like this example here. We're starting with an acid and a base, and we end with an acid and a base. The acid that we end with is going to be the conjugates, the acid and the base. Okay, so we have a pair on the bottom here, the H2O and H3O plus. So H2O and H3O plus is just one hydrogen off from each other, so they're a conjugate. Our other pair, CH3COOH and CH3COO minus, it's just that last hydrogen's missing. So it's also a second pair. Notice how the pairs have one weak, one strong. So a weak acid becomes a strong base, weak base became a strong acid. Okay. So that's what the conjugates are, it's just the pairs that go together. Okay. So let's label these. So for these two here, we're going to label the acid, the base, the conjugate acid, and the conjugate base. Okay. For this first one here, we have an NH4 plus that has an extra H with a plus and an OH minus. So the plus is going to be our acid, the OH minus is going to be our base because our NH4 can give away a hydrogen. Now let's look for our pairs. So NH4 is closest to NH3, so that's going to be our conjugate base. And then our OH minus is close to our H2O, because remember that's the same thing as HOH, so we have the OH there. So it's our conjugate acid. Okay. For the second example, we have HSO4 minus and H2O. This one's a little weird because HSO4 minus, it can lose that hydrogen or it can gain a second hydrogen. H2O can lose that hydrogen or it can gain another hydrogen to make H3O+. Okay. So these can both go either way. So what we're going to do is look how it compares to its conjugate and then see what's happening there. So HSO4 minus loses the hydrogen. If it loses the hydrogen, that makes it its acid, and its conjugate is going to be the conjugate base. H2O is gaining a hydrogen, that makes it a base. Its conjugate is the conjugate acid. Okay. So sometimes we can't just know straight off the bat from the start. You sometimes have to look how it matches with its conjugate first. All right. And then with acids and bases, we do have some math. This math here is on your periodic table, all these, or not all the equations, but a version of all these equations. So you'll have that pH equals, or pH plus POH equals 14 on your formula, but you won't have these two down here on the bottom, right? Because those are just manipulating that equation. All right. So these equations is just converting between these different factors. You have, these should be concentrations of H plus and OH minus, and you're converting between those two, between pH and between POH. Okay, so these are the pH and POH scales that we were talking about. Okay, so the math for this is you plug into the equations. All right, so we're not going to go too deep into that. We'll do some examples on the next slide. But to help you understand these a little bit, for pH and POH, so on the bottom of the box of our square, it's an exponential function. So for each pH level we change, the acid is going to be 10 times stronger or weaker. So if we go from a pH 5 to pH 4, we're changing by 1, so it's 10 times stronger. pH 5 to pH 2, we're changing by 3 there. So 10 to the 3 is 1,000 times stronger. If you go the opposite direction, if we go from 2 to 5, right, it's becoming more basic, so it's 1,000 times weaker. For a concentration, it's just a 10 times scale. It's not exponential. So if you change the concentration by 10 times, if you make it 10 times stronger, so from 0.001 to 0.01, it's 10 times stronger there. Okay, so let's do some practice with this math here. I'm gonna do the second two. I want you to do the first one. If you know what you're doing, go ahead and do it. If you're not sure, see what I do for 2 and 3, and then go back and do the first one. Okay, the first one's going to be the easiest one here. For the second one, we are looking for what is the H plus concentration if we start with a POH of 9.88. So in our square, we're starting on the bottom right, we have a POH. We're going to the top right, top left, we're going to H plus. So we need 2 steps here. What I'm going to do is I'm going to do we're going to go to pH first. pH equals 14 minus my POH, which is 9.88. And that gives me, let me do this in my calculator, minus 9.88, 4.12. So that's my pH. And then I can do H plus equals negative log, or sorry, not negative log, equals 10 to the power of negative pH, which is 4.12. And that gives you an answer of 7.59 times 10 to the negative 5. We're looking for concentration, so our units are molarity. Okay, so what I did is I went left first, then I went up. Okay, you can go the other way. You can go up first, then to the left. It doesn't matter. Whichever path you take, it does not matter. As long as you get there in the end, that's what matters. Okay. For the second question down here, we have what is the pH. So we're looking for pH of a solution with 3.35 grams of NaOH in 1.15 liters. Okay. So from this, we can get that to molarity of NaOH. I'll show that here in a minute. But on our square, we are looking for pH. We're starting with the OH minus concentration. So again, we have two steps. To get this to molarity, right, we need moles first. So 3.35 grams divided by the moles. And if for the moles, we have 23 for sodium plus 16 oxygen plus 1 for hydrogen. So it has a molar mass of 40. 3.35 divided by 40 is 0.08375 moles. Okay, don't forget your units like I am. All right, then to get to molarity, we divide the moles by the liters. So that divided by 1.15 gives me 0.0728 molar. And this molarity is for NaOH. But NaOH is a strong base, so it fully dissociates. So it's also the molarity of our OH minus and our Na plus, but we don't care about the Na plus. Okay, so we have our molarity. Now we need to get to pH. So for molarity, I'm going to go to POH first. So my POH is negative log of my molarity. So negative log of my molarity in my calculator gives me 1.1377. Then my pH equals 14 minus my POH. 14 minus that gives me 12.86. Okay, and pH does not have any units. All right, so I want you to go back and do the first one if you haven't already done that. You should get an H plus concentration of 4.8 times 10 to the negative 4 molar. All right. Okay. I want you guys to also do this question here. I am going to start it with you though, just to make sure we start it correctly. But we're looking for the pH of a solution. We are given a 10 milliliter solution of 0.002 molar KOH is added to 10 milliliters of distilled water. Okay, so to do this, we need to find the moles of KOH first, or moles of OH minus, and then go to the final molarity of OH minus with the 20 mils. So this was from the 10 mils, and then we go to 20 mils. Okay, so for the 10 mils, to find the moles, we're going to multiply them. So multiply the 0.01 liters times the molarity. So 0.010 liters times 0.002 molar gives me, let me do my calculator, 2 times 10 to the negative 5 moles of OH minus, because remember this dissociates completely. It's a strong base, so KOH becomes K plus OH minus. All right, and then to find the molarity of OH minus at the end, we're going to do our 2 times 10 to the negative 5 moles that we just got, divided by my 0.020 liters, because now we're at 20 milliliters. Okay, so that divided by 0.02 gives me 0.001 molar for OH minus. Okay, so now I can do the same thing I've been doing before. Okay, so you're going to go from the 0.001 molar OH minus and figure out how you're going to get to pH. All right, after you do that, you should get the answer as B, 11. All right. Okay, so a couple more vocabulary words before we get into equilibrium. Amphoteric means that a substance can act as either an acid or a base. So this is what I was showing earlier, where H2O, it can gain a hydrogen, so it can act as a base to gain a hydrogen to become H3O plus, or it can act as an acid and lose the hydrogen to become OH minus. Okay, so all of these can do the same thing. H2PO4 and HSO4 can both do the same thing. They can either gain a hydrogen or lose a hydrogen. Okay, Okay, that makes them amphoteric. So they act as either an acid or a base. Polyprotic means that you have more than one hydrogen or hydroxide. Protic normally does indicate hydrogen, but you can also use this word for bases with hydroxides. So if you have something with more than one, so like H3PO4, H2PO4 minus, those are polyprotic, they have more than one hydrogen. With bases, right, if you have calcium hydroxide, you have more than one hydroxide there. It's polyprotic. Right? So make sure you understand those vocabulary words. We'll use both of them more in this lesson, okay? But polyprotic, especially during the titration part. Okay. So going into equilibrium, we're going to start with strong acid, strong base first. With a neutralization reaction, if you're putting an acid with a base together, we need to use this equation here to determine an unknown molarity. Okay, if something is polyprotic, you multiply the molarity by the molar ratio. So if you have H2PO4, you're going to multiply the molarity by 2 there. Okay, we'll see that down here in this example. All right, but this equation here, M1V1 equals M2V2. M1 is your first molarity. V1 is your first volume. So it's for one substance. M2V2, your molarity of that substance times the volume of that substance. Because remember, during a neutralization reaction, we want them to be equal. We want an equal concentrate or equal moles of our H plus and OH minus. All right. So what that looks like is down here. If we have volumes of 0.200 molar H3PO4, and you're neutralizing 0.200 molar NaOH, that's a strong acid and a strong base. We're going to use the equation. M1V1 equals M2V2. Okay, we're looking for what volume of H3O plus. We're looking for that volume there. So my molarity is 0.200 times my V1. My second molarity is 0.200 times my 100 milliliters. With this equation, you don't need to change to liters. As long as your volumes are in the same units, it does not matter. Okay. So if you do this equation here, and just really quick, actually, I just mentioned this for polyprotic, we need to multiply our molarity here by 3 because we have 3 hydrogens. So really, this is 0.600 there. Okay. So my 0.600 times V1 is equal to 20. And I'm going to divide the 0.600 over. So 2 divided by 0.6 gives me 3.33. Let me just make sure I did my math right. No, I did not. Yeah, so this should be 33.33. Okay, and since we had milliliters, the volume here is going to be milliliters. Okay, so for strong acids and bases, make sure you remember this equation. That equation is not on your formula sheet. You need to know that equation. But that will be used for strong acid and bases. It's pretty straightforward there. If you have a weak acid or base, you're using equilibrium, just like we did before. Okay, so we have 2 equilibrium constants. We have the Ka and Kb. Again, it's an equilibrium constant. It's products divided by reactants, but A just means it's for an acid, B means for a base. Okay, so the bigger Ka or Kb, the more products you have, so the stronger the acid, the strength, or the stronger the base. Okay, so on the right here, we have our K and Kb expressions. Notice that H2O is not in the expression because it's a liquid. We don't add liquids into our equilibrium expression. Remember, solids and liquids do not get added, only aqueous and gases. Okay. All right. So we have equilibrium expressions. So let's write them for these down here. NH3, we need to write the equation first. NH3 is a weak base. So NH3 plus, let's add some water in there, becomes NH4 plus and OH minus. Okay. So our water is a liquid. We don't add that in our equation. So my KB, because this is a base, is my products, NH4, sorry, that's bad handwriting, my NH4 plus times my OH minus divided by my NH3. Okay. For the second one, we have HF. Let's add some water in there. Remember, this is a liquid. This becomes H3O plus and F minus. Okay. So my Ka expression, because this is a weak acid, has an H. It's donating the H. Is my H3O plus and F minus divided by my HF concentration. Okay. If you did the acid without the water, so it becomes H plus and F minus, that's also acceptable, either one. But acids and bases are normally done in water, so I'm just used to adding them, but you don't have to if it can be done without it. All right. So you have a Ka and Kb expressions. Same thing we did for equilibrium. We also have a Kw. Kw, we've seen this equation before, right? The H3O plus times OH minus equals 1 times 10 to the negative 14. So at 25 degrees Celsius, and that temperature comes up later, but at 25 degrees Celsius, our Kw, so this is the autoionization constant of water, so it's just water breaking down on itself, is 1 times 10 to the negative 14. Okay, so that means our OH minus concentration and our H3O plus concentration multiply to make 1 times 10 to the negative 14. Okay, that means if one increases, if our H3O plus increases, our OH minus is going to decrease. It's a directly proportional relationship. Okay, Kw is temperature dependent though, because it is an endothermic process to break the bonds. Okay, so remember we said Ks can be influenced by the temperature. So what happens though is your ratio of H plus to OH minus is not changing, right? Because H2O still goes into H3O plus and OH minus. What does happen is what's considered neutral changes. So if you increase the temperature, your neutral is now less than 7. If you decrease the temperature, your neutral is now greater than 7. Okay, so it's a weird concept, but all is, if you change the temperature with Kw, it's just changing what we consider as neutral, just changing the baseline. Okay. All right. So this slide looks like it has a lot on here, and I'm sorry about that. But with acids and bases, right, we have the acidic, neutral, or basic salts. The pH is going to be based on the conjugate acid or base. Okay, so whenever you have a reaction, the pH is going to be based on the conjugate. So looking at this really quick, this little chart here. If we make a salt, so if you make like NaOH plus HCl goes to H2O plus NaCl, right? If we're making a salt there, if the salt is acidic, right? So NH4 plus with a Cl minus, it's an acidic salt. It's an acidic solution at the end. If it's neutral, right? Na plus and Cl minus, those are both neutral ions. It's a neutral salt. The solution is going to be at pH 7. If you have a basic salt, it's like CH3COO minus, that comes from an acid, right? So it's a basic salt. Your solution at the end is going to be base or basic. Okay, so the solution at the end is determined by whatever your salt is that you make. Okay, so when we're talking about the pH of solutions and the strength of a solution, we can talk about which has a we can talk about Kw and Ka, the equilibrium constants. Okay, if you compare equilibrium constant, if you multiply them, that should be equal to Kw, the 1 times 10 to the negative 14. Whichever is larger controls the pH. So if your Ka, so let me do this real quick. So if we divide that, or if we take the square root of that, so square root of 1 times 10 to the negative 14 is 1 times 10 to the negative 7. I couldn't know that in my head, that's okay. So breaking even is 1 times 10 to the negative 7, if they are equal. If we have one that is greater than this number here, the greater than 1 times 10 to the negative 7, so say Ka is 1 times 10 to the negative 6, we know that the solution is more acidic because the Kb would be 1 times 10 to the negative 8. Okay, so that's what that is meaning. All right. And then another concept we have here is pKa and pKb. So remember, if you add the p in front, that's the negative log. So pK is negative log of Ka, pKb is negative log of Kb. Okay, so pKa and Ka are oppositely related. If your Ka is high, it's a strong acid. But if your pKa is low, so relatively lower than 2, that's a strong acid. Okay, same thing with pKb and Kb. High Kb is a strong base, but low pKb is a strong base. Okay. And then we also have that pKa plus pKb is equal to 14. The same way we had pH plus pOH equals 14. All right. And we can compare things like pH to pKa. If our pH is less than our pKa, the protonated form will exist. So the acid stays together with the hydrogen. If pH is greater than pKa, we'll have the acid deprotonate. The H plus goes away. All right, so a lot of information on this slide. pKa and pKb is a hard concept to understand. So if we have questions about that, make sure to write them down so we can ask them. Sorry about the bells, but let's look at this question here. Okay, this question is kind of long. We have a student pours a 10.0 milliliter sample of a solution containing HC2H3O2, which has a pKa of 4.8, and NaC2H3O2 into a test tube. So we have an acid and its conjugate in a test tube. The student adds a few drops of bromocrystal green to the test tube and observes a yellow color, which indicates that the pH of the solution is less than 3.8. Based on this result, which of the following is true about the relative concentrations of HC2H3O2 and NaC2H3O2? So we have a pKa and we have a pH. Right, our pH is less than our pKa. We just said that if pH is less than pKa, the protonated version will exist. So the protonated version is our HC2H3O2. So our HC2H3O2 should be greater than our NaC2H3O2. Okay, so make sure we understand that relationship because it makes questions like this really easy to do. This looks like a complicated question, but you just need to compare the numbers. All right, moving on to titrations. Okay, we're gonna have two more concepts, right? Titrations, then Henderson-Hasselbalch, and that's the end of this unit. I know it's a long one. Okay, so for titrations, a titration is a quantitative analysis. So quantitative means that we're using numbers to determine the concentration of an unknown solution. Okay. So an example of a titration graph is here is on the bottom. The one on the left is for a strong acid, right? We start with our strong acid. We're going to add our base so it increases the pH, and then we get to a point where there's no more acid. It's just the base, nothing else. Okay. So some parts of this graph that are important. We have our equivalence point. That's where the moles of acid and base are equivalent. Okay, so it's labeled here. That's at the center of that peak, that stretch. And that volume is important. So 25 milliliters there for that one. Okay, at this point, we have what's called an indicator. The indicator changes color. So if we look here, This is phenolphthalein. Phenolphthalein is normally clear. When you're at the equivalence point, it's that very pale pink color. If you go too far past the equivalence point, if you overshoot it, it becomes this bright pink color. Okay. So at the equivalence point, that's when our moles of acid or base are equivalent. That's when our indicator changes color. Right. The half equivalence point is what it sounds like. It's half of the equivalence point. So half of 25 is about 12.5. That's our half equivalence point. At the half equivalence point, our pH is equal to pKa. Okay, that's written there for you. And the concentration of the acid, so our acid, our HA, is going to be equal, let me write this up there. Our concentration of the acid is going to be equal to the concentration of the conjugate base. Okay. And then the last term is our endpoint. The endpoint is that plateau at the end where it's reached completion. You only have bases in solution. Okay. So this is for a strong acid and a base. You can also have it as a base with an acid, where it's going the opposite direction. Okay, just based on what you're doing the titration with. You can also do it with a weak acid. So with a weak acid, you start up at a higher point. This little curve here, this section here, we'll talk about in a minute. It's called the buffer region. That will be a little more elongated, but it's the same idea. Okay, and then really quick also, remember we talked about polyprotic. So if you have something that's polyprotic, so H3PO4, you have 3 hydrogens. During a titration, you're going to remove those one by one. So you can see we have 3, oh sorry, I spelled it wrong. We have multiple parts of the graph. Okay, so the parts of the graphs, there's 3 sections. Those are for the 3 different hydrogens. They have different titration values. Okay, so if you have a polyprotic compound, you'll have more than one curve in your graph. If it's monoprotic, it's just a simple single curve, like an S. Okay, so really quick in this graph here, if we have a titration with an aqueous solution of a weak base B with HCl as a titrant. Okay, so we're doing a titration with a weak base and a strong acid. Based on the graph, which of the following estimates the pKa of Hb+. Okay, so what is a pKa of Hb+? Remember that pKa is half of the equivalence point. So if our equivalence point is at 50, our pKa is going to be halfway. That's going to be at 25. So our pKa there is at 11. So 10.8. Right? Okay. And then talking about buffers, what a buffer is it's a solution that resists the change in pH. So for a buffer to happen, you need to have either a weak acid or a weak base. Okay. Some examples of this is like bicarbonate buffer in your blood. It helps maintain your blood pH, because if that wasn't there, your blood would fluctuate and that would be really dangerous to us. You also, in personal care items like shampoo and lotion, they contain buffers so that it doesn't cause irritation to your skin. Okay, so buffers are in a lot of different places. You also have buffers in your stomachs for the stomach acid, right? It's just resisting changes in pH. It keeps it at a pretty close range of pH. Okay, so they do this by reducing either the H plus or OH minus that's added. So it's essentially just taking it up so that the H plus and OH minus is no longer in solution, so it can't affect the pH as strongly. Okay, the ideal buffer should have a pH or pKa close to your equivalence point. Okay, so an example of this is if we have a solution of HF and NaF, the HF dissociates into H plus and F plus. Okay, with a strong base, if you add the OH minus, that H plus reacts with the OH minus, taking it away, so that this here, the H plus and NaF, that's our buffer solution. We're adding our strong base, and the basic part is being taken up by the buffer. Right? Okay, so let's look at this question here. If we have the acid ionization equilibrium for HF as represented by the equation above, a student claims that the pH of the solution that contains 0.100 molar HF and 0.100 molar NaF, so it's a buffer solution, will change only slightly when small amounts of acid or base are added. Which of the following pairs of equation can a student use to justify the claim? So we're looking for both acid and base only having small changes. So let's look at this. For A, we have HF plus OH minus makes H2O and F minus. This is what we said, the H plus goes with the OH minus, so that part's good. The second half is OH minus plus H3O plus makes 2H2O. Well, we don't have our HF or our NaF there, so that's not the right answer. This second part does not work. It doesn't show that the solution we have is a buffer, even though it does neutralize it. The second equation, or for B, the first one here, we have the same thing. We don't have the NaF or the HF, so that's not the right answer. The third one, this first equation, we have that H going with the OH minus, so that works. The second one, we have the F minus going with H2O to make HF and OH minus. Okay, this is just the backwards version of what we just saw, the first equation. This is making OH minus. We wanted to get rid of the OH minus, so that's not going to work for us. For D, we have the HF with OH minus, so that one works as usual. The second part, we have the F minus with the H3O plus, and that neutralizes it. So it's taking away both the basic part of things and the acidic part of things. So that is going to be our right answer. Okay. And then our last topic for these notes is the Henderson-Hasselbalch equation. So for weak acids and bases, because they do not completely dissociate, we need to perform a calculation based on the pKa or pKb, as well as the ratio of the conjugate and the initial substance. Okay, so this equation is called the Henderson-Hasselbalch equation. You'll notice it's the same thing for pH or for acids and bases. The only difference is that a pH you use POH, that a pKa you use pKb, and then it's just the conjugate and the initials flipped, right? But it's the same exact equation. This equation is on your reference sheet. And just a note, I didn't mention this before, but for your reference sheet, these are under the equilibrium section. I don't know if I mentioned that, but this is under the equilibrium section. There's no acid-base section, okay? So what you're doing with this equation is you're taking the ratio of your concentrations of your base or acid. Okay? You can also use moles there because this is just a ratio. So taking the log of the ratio plus your pKa will give you your pH. So we often use this to either find the pH or the pKa. Okay. So let's do an example with this. If we have a student prepares a lactic acid sodium lactate buffer solution by mixing 40 milliliters of 0.05 molar HC3H5O3 with 200 milliliters of 1 molar NaC3H5O3, we have a pKa of 3.08. We're looking for what is the pH. Okay. So the equation is pH equals pKa plus log of our, so we have an acid and a conjugate base. So this is going to be the conjugate base, and then put Cb. So the concentration of our conjugate base divided by the conjugate, or the concentration of our acid. Okay, so we have all these numbers. So pH, we said our pKa is 3.08, and then we have the log, our conjugate base. So we have a different volume, so we do need to change these to moles. Okay, so for our conjugate base, that's this one here, the 200 mils of 1 molar. So to change that to moles, the 1.0 molar, we're going to multiply by 0.2 liters. Okay, we 1 times 0.2 is 0.2. Okay, for our acid, we have this one here. So the 0.5 molar times my 0.04 liters is 0.02. Okay, so my conjugate base goes on top, 0.2. My acid goes on bottom. Okay, so if I do my 0.2 divided by 0.02, that gives me 10. Log of 10 is 1. And if I add 1 to my 3.08, I get 4.08. Okay, so that is how you're going to use a Henderson-Hasselbalch equation. All right, so we will do a titration lab in class, so that'll hopefully help you understand how titration works if that was still foggy for you. But make sure we understand the math for this. There's a lot of different terms that look very similar here, so this can get quite confusing. Okay, and the last year, the hardest units from the students were equilibrium and acid base for this reason. Okay, so make sure you study, ask questions if you need help. But we only have one unit left, electrochemistry, and we'll be done with the lessons. That'll be it. All right, so I'll see you in that video. Have a great day.